let's have a look at these. So I think we did stuff like this yesterday. So which one of these is shorter, going to be quicker to do? Number 2 and y. Let's see if we can describe this using some vocabulary, because we're doing what? Distributing a, what can we call this? How many terms is it? 1, so in Latin we call that a monomial, right? So monomial, we're distributing it to a trinomial, so we're only going to get 3 terms, right? This time we're taking a trinomial and a trinomial. What kind of trinomials are these? The ones we saw before, right? They're quadratic. Good, 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 good. Good. Okay, so this one's going to be faster, so let's do that. We'll only get 3 terms. 1, 2, and that last one, 3. Okay, so the first term, what is that? It's going to be 4. We've got 5 f's. I always, if you're having trouble with your rules and stuff, just think about how many f's are here. Like you could spread that out and say it's 4 f's multiplied together, right? Then you've got 1 more, so it's 5. That's what I always do if I'm questioning myself. And then g's just attached, yeah. And then this times this is going to be 8. How many f's do we have? F times f times f times f is 4 f's, right? And 2 g's, g squared. I should be careful when I say that, because is 2g the same thing as g squared? It's not, right? Like I'm trying to say, when I say 2 g's, I mean like g times g, right? Got to be careful with the language. Okay, so then this one, 4 times negative 1/12 is going to be negative, right? 4 over 12, what's 4 over 12? 1/3, okay. And then we've got 3 f's, or f times f times f, and same thing with g's. Done. Unless any of those go together, do they? Remember, we want to think about these as types of objects. What types of objects do we have here? We have f cubed, g cubed objects. Yeah? I don't see any more f cubed, g cubed things, do you? These are f5th g objects. These are f to the 4th g squared objects. We've got 8 of those, 4 of those, negative 1/3 of those. That's how we want to think about these, okay? All right, this one's going to take longer. I think I'm just going to write it out, otherwise we're going to be here talking about it all day. Okay, so let's see. I'm going to go x squared times all of them. So we get that, and that, and that. Okay, so I'm going to cross some stuff off. He's done. Then I'm going to go here and say negative 7x cubed.
Did you put it underneath? Because then you like know which ones line up together. Like if you
How
put
have you
the
done
cubes in line.
Kind of like make a matrix.
Yeah, kind of. But that's like how Mr. Brooks.
So he does like this one.
Yeah, and then you
with
put
those
it in
3.
line, and then you just do one. You skip the x to the 4th, and then you just put the negative 7.
Oh, that's nice.
Cube underneath the.
So you're like already kind of doing like
Yeah,
terms at the same time. You guys know what she's saying?
Yeah.
I think she's saying, well, I mean, some of you have done that, some of you haven't. So I mean, it's up to you. I just go she's saying like kind of prepare yourself for later on. If you go x to the 4th and then you say x cubed and then x squared, and then you be careful, you can like line stuff up and have like terms kind of descending. You don't have to do it that way though. It's up to you. That might be more elegant. Mr. Parks is pretty elegant from what I've seen, so that's why he does things that way. Yeah, I made a mistake already though. Could somebody spot it?
It's not negative 7x. Wait a minute.
That's not it. Somebody spot it. Miss Crane, I need you to spot the mistake.
Oh, it's.
Didn't distribute
I'm. Give it. Let's see if Mackenzie can find it. We're all finding it. Good. I did these 3, and then I went to this one. Okay. So in those 4 so far, there's one that's wrong. Not this one. Okay, Rachel was up first. Where is it?
3x squared.
Oh gosh, dang it. That is 3x squared, isn't it? Okay, so then I did this one, and then we need to do this one, so it's positive 7x squared, and then do this one plus 21x, and then we've got the 5. So we did all those. We're getting 9 terms though, right? So then we've got 5, that's easy, 5x squared minus 5x minus 15. And if I was elegant, I would have lined these up, wouldn't I? I'm not so elegant sometimes. So then we say, okay, do we have any more 4th degree things? No. Done. 3rd degree things. We have this one and this one. How many of them? Negative 8 of them. Yes? X squared things, we got a bunch of those right there, there, and there. So we got 4 of them between these two, and 5 of them is 9 of them. Okay? X things, we've got those two. So 16, is that right? Yeah, and minus 15. Done. I like the lining them up suggestion though, that's pretty good. But you don't have to. Okay, let's try this one. So it says the cost of, I thought this came out well if we thought of this in terms of TVs, if you see what the answers are. So this sounds like it would be right for manufacturing TVs. It says this polynomial approximates like how much money it costs to make them, right? This has nothing to do with sales. That could be a whole nother situation. So this is like cost to manufacture them. But what's tricky about it? X is in hundreds. They've like redefined X in a different unit. You gotta be careful with things like that. We talked about order of magnitude yesterday, didn't we? Like powers of 10. So what powers of 10 is M measured in? 10 to the 2nd power, right? Cool. All right, so M of 0 we can just do it in our head, right? 0, 0, we get 45.
Why does it cost $45 to make
For lights.
0
To light up the factory.
Exactly, we're supposed to explain it to you, right? That's the main point of this. So good point. So why does it cost $45? Do we know that this is just in dollars? Did it say what units M was in? It didn't. What do you think this is more likely to be? Let's try to make this more realistic.
Wait,
If we're running a TV factory and we're lighting that factory and heating that factory and paying for the electricity and other things, it wouldn't just be hundreds of dollars. So we said X was the 10 squared order of magnitude. What do you think M is in? Maybe 10 to the 4th? I bet it's more than that. I bet it's like 10 to the 6th, 10 to the 5th. At least 10 to the 5th, hundreds of thousands of dollars just to operate that factory. Maybe I'm wrong though. Maybe those Chinese are more efficient than I think they are. So I don't know. The Koreans, they manufacture most of our TVs. Koreans do. So let's say, let's go with what Courtney said. She had the best one. So 10 to the 4th. 10 to the 4th is what?
1,000, 10,000.
10,000. So we're going to say it's like 10,000s of dollars. So this is really what then?
45.
You can think of it like this in scientific notation. Does that help? So is it 45,000 or $450,000? And that seems okay to me. It would cost a lot to run a factory that produces high-tech stuff. Okay, good point though, Derek. All right, M of 200, what is that? Let's put that in our calculators.
8 million minus 36,000 plus 40.
Remember, don't touch this order of magnitude until the very end. Just stick 200 in the polynomial. So what is that? I need somebody to tell me.
3x cubed is 8 million.
I want the whole thing though.
Oh, 8 million minus 36,000 plus 45. 79,000.
I remember the book said this. I mean, what was it, Maggie? I heard you.
it's 23,996,445.
Oh, I didn't multiply by
I just did it
6.
right.
23,99.
Then you gotta multiply by 10,000.
4, 4.
2, 4.
5.
Okay, it's not perfect anyway. This is just an estimate, right? I mean, it's definitely not perfect. So, but we're going to translate that now into real money by multiplying by the order of magnitude, which is 10 to the 4th we decided on, right? The problem didn't have this. The problem was like fake. So.
It's 2.3 to the times 10 to the 11.
Ah, so right now, look at this number. What order of magnitude is this? Right? Am I going to be real particular on your assignment if you get this perfectly? No, but I'm trying to teach you some stuff that'll be useful in your science classes and stuff, yeah? So this is 10 to the 3rd because it's thousands, right? This is 10 to the 6th, millions. So this number is 10 to the 7th. So you put another 10 to the 4th on it and you get, let's just say approximately 10 to the 11th, which isn't that like hundreds of billions of dollars? No, I think we made a mistake. Something's screwed up. But you know, we kind of made this problem up. It's good to think about how big things really are and stuff.
Yeah, they're like the movie screens.
Yeah.
That's what they're making.
They make the big giant movie screens.
I don't know. Would they still be able to make a profit though if their costs are $11 billion? If they were actually able to manufacture 200 of them, maybe they'd sell them for a lot. Like maybe these are like the jumbotrons, unlike the other
Sell for
stadiums
$1 billion
or something.
each.
So maybe, I guess. There better be some pretty big TVs though. So
Yeah.
okay, good. So the key on those, you guys have a couple problems where it just says, you guys have a couple problems where it just says, here's a polynomial, you know, make a couple predictions. That's going to be really easy. The key you're going to focus on is what? How to predict what that is. So you're going to write me like a little sentence or something like that that says, for 0, the cost of manufacturing that many TVs was 45. You don't have to worry about this order of magnitude thing because of, remember what Derek said? Because it costs some to open the factory for lights or whatever, okay? And then you'd say to produce 200, it would cost this much, because that's how much it costs to produce that many units, okay? That's
What if you use 10 to the 3rd?
Try to think about it though. Don't just give me bland random answers.
I think 10 squared would be the better one because.
Yeah, that might have been a better
10 squared because $44,500 might be enough to light a factory.
Yeah, you're right.
Especially in Korea.
I was thinking 10 squared at the beginning, but I was like, oh, I don't know. Tough to say. Okay, the 2 last ones, and you guys will have some time.
Is that okay?
Okay, we want to do something pretty simple with this. We've got a couple polynomial functions, right? Degree on this is, and that one is 4. Okay, so we're going to start to explore what those look like today, just a tiny bit. We're not going to get into it too much. We're going to put them in our calculator and see what it says they look like. So go ahead and graph those if you would. Just one at a time. Let's graph the cubic first. So throw that cubic into y equals. Let's see what it looks like. Then we're just going to describe it kind of primitively, just a tiny bit. Just so we can start to get an idea of what polynomials look like, and we'll refine that as we go. Okay, I put it in my graph, and I got something like this, so make sure you're getting something like this. We're not going to be real particular about the scale or anything right now. You getting something like that? Well, that's what a lot of cubic curves look like. They kind of look like a snake. We'll get a little bit more specific here, but not today. So how can we describe what's happening here? I think we want to say like left to right what's happening. So I don't know. We can talk about how many zeros it has. We can talk about where it's growing, where it's not growing. So how about we say this? What's it doing at the beginning? Growing or not?
Growing.
Okay, so we're going to say, what's the technical word for that? Increases, there we go. So first, f is increasing. We could even use our calculator to like get this thing for us, couldn't we? We know how to do that. We'll go through it another day, but we could definitely get this value precisely and make it precise. But let's just be general today. Okay? So f is increasing until that spot, right? Then what happens right after that maximum? It's decreasing until when? Until the minimum. Great, but let's just say first f is increasing. You can say to the maximum if you want, but then it's decreasing. I'm just being pretty general today. And then what happens? It's increasing. Then f increases. Let's be a little more specific, maybe. Out to x approaching infinity, right? Because it's got an arrow. It's going to continue increasing forever after that, right? So we could be a little bit more specific, but not too much today. So I think that's good. We should talk about the zeros. How many zeros does this have? 3. We can't see imaginary zeros though sometimes. We're going to just say 3 real zeros, okay? So maybe with 3 real zeros. As always, sentences should be complete, right? So is that complete? Yeah, I'm trying to. It's good. Okay? I don't want to be too bad with our English. I find that's bad. You guys know that last time I taught AP Stats, did any of my kids have trouble? I shouldn't say my kids. Did any of the students have trouble with the math? At all? There was one person who had a little bit of trouble with the math sometimes. What did they have trouble with? And they're not like word problems like we're doing in here. It's more of just like what's happening in this situation. It was the reading part. That's what people have trouble with more often. So we're going to be a little more particular this year. Okay, 4th degree. What's that one look like? Do we have it in our calculator? Do you have it, Courtney?
Yeah, it looks like a W.
It looks like a W? Okay. A skinny W? Okay, so something like this. I got something like this. Cool, so that must be something to do with what 4th degree things look like. Actually, knowing what they look like is pretty easy. Don't want to overload you. So let's describe this one. We should say first H is, what's it doing first, left to right? Decreasing. We could even figure out where this is. Should we do that this time? Let's do it this time. So tell x equals, what's the x value right here? Somebody calculate it for me. I want the exact value. So you'd be calculating a what? Minimum, right?
Do the minimums always have to be the same? Are they always the same?
Ah, good question. For
It's
polynomials, no.
Negative 1.41.
This is a symmetric one, but not always.
X is negative, wait, I feel like I have this wrong.
We'll ask for someone else too,
No,
Rachel.
that's right.
What do you got?
X is negative 1.414211 and Y is negative 1.
Cool. So we could do that for each one of these, right? But we'll just keep going after that. So it's decreasing from negative infinity out to that spot right there, right? Then it's increasing up until it looks like where? Then H increases until x equals, I think it's 0, isn't it? Until that looks like it's 0 to me. We'll just say it's 0. And then does it look like it's symmetric? Does it look like it's identical on both sides? Sometimes polynomials are like that, does it? You guys tell me.
Yeah.
So I think we can, let's just assume that,
It decreases until x equals 1.414.
yes, you guys hear Katie? And then finally it increases. So, and finally increase. This is a run-on sentence, jeez.
Until x equals infinity.
We can't really get to infinity though, so we can't say equals, we have to put an arrow. We can't get to infinity, right? You can keep trying, will not be successful. So you can't put equals infinity. Does that make sense to you guys? It's a big no-no, you never put equals infinity. It's bad. How many zeros? How many real zeros at least?
4.
4. So there's a theorem we're going to do soon, probably next week, that says like how many zeros any kind of polynomial has to have. It's a pretty nice theorem. What do you guys think that theorem might say? This one had 4, that one had 3. Maybe it has something to do with the degree. Maybe it's always the same amount. But here's the problem. Parabolas are degree what? 2, and sometimes parabolas did
No, we also have
that. So is it always equal to the degree? No, but it's something like that. Okay? Cool. We're done.